Dear friends, Jacobian is a very important quantity that arises in multivariable differential calculus. And it has got quite a good number of applications, but two of them are significant. And of that, one of them I'll be using for multiple integration. So, if you have a transformation, let us say, that connects two variables uv to two other variables x and y. So the variables u and v are connected to two other variables x and y. Then the Jacobian is given by a determinant where we have the partial derivatives of u with respect to x and y in the first row. This is dou u by dou x, this is dou u by dou y. And then the partial derivatives of v in the second row. So things will work out only when this Jacobian is not equal to 0. And this Jacobian can be a simple number, in which case it's very easy to interpret what's happening. But when the Jacobian is a variable quantity, then the interpretation takes a little bit of effort. So basically, whatever I've written here, in another notation can be written as dou uv upon dou xy. And this means du dv divided by dx dy is equal to j. So if you have j dash as dou xy by dou uv, then this would be dx dy by du dv. The reciprocals of each other. So which means that j times j dash would be 1. This can be exploited because we can write this as j is 1 upon j dash and j dash is equal to 1 upon j. Of course, I assume that neither j nor j dash are equal to 0. Only then it's a valuable tool. Now, how is it useful? Where is it useful? So Jacobians are used at least in two contexts. One, in finding derivatives of implicit functions functions can be regarded in two ways, implicit functions and explicit functions. So when the relationship between x and y is extremely complicated, that you cannot write one in terms of the other easily, we brand it as an implicit function. And for such situations, if you want to get the derivative, dy by dx or dx by dy, then the Jacobian can be used as a very important tool. Of course, that is not in the present area of our interest. The second application is in evaluating multiple integrals when we seek to change the domain of integration, or let me say to change the variables in the integration process. So the focus of this presentation is how Jacobians are used in the evaluation of double integrals when we want to change the variables. Of course, you should understand that you cannot, for the sake of changing variables, you do it. There must be a necessity or a need for that. Otherwise, a very simple situation can become complicated if you keep on changing the variables. It should be the other way around. A complicated situation must become simple when you change the variables. So let me explain this application of Jacobians today. So suppose we have evaluate double integral square root of x squared plus y squared dA, where R is described by y greater than or equal to 0, x squared plus y squared less than or equal to 16. So let us interpret this language. Y greater than or equal to 0 means the region is above the x-axis, because y is equal to 0 represents the x-axis. Y greater than 0 would be some region above the x-axis. And then you have x squared plus y squared less than or equal to 16. If you take x squared plus y squared equal to 16, that would be a circle. With center at the origin and radius 4 units. So this would be 4, 0. That would be 0, 4. This would be minus 4, 0. This would be 0, minus 4. This is x squared plus y squared equal to 16. Then this is the region corresponding to x squared plus y squared less than 16. Less than means the interior of. So suppose the problem is to perform this double integration over this region. So doing this in Cartesian variables is not advisable. So we convert it into polar. So I'll write transform to polar coordinates. How does that happen? It happens through the transformation equations. X is r cos theta, y is r sin theta, and as immediate consequence of this is x squared plus y squared would be r squared times cos squared theta plus sin squared theta, which reduces to r squared. How is this useful to us? The x squared plus y squared here would be reduced to r squared. Not just that, now comes the Jacobian. This is the reason why I have selected this topic. Jacobian of this transformation We'll have xr, x theta in the first row. Because there I had explained when the UVs are getting converted to XYs, then you will have first row having UX and UY as partial derivatives. So here XR and X theta, similarly YR and Y theta. It is assumed that your partial differentiation is decent. XR would be to differentiate X with respect to R, and then you will get 1 times cos theta, it's cos theta. Differentiation of X with respect to theta means you have to differentiate the cos theta function. You will get minus sin theta, but this is a constant. So you write minus r sin theta. Then we go to the next row. YR would be 1 times sin theta, and Y theta would be to differentiate sin theta, which becomes cos theta. But don't forget you have to copy the r, you will get r cos theta. So this will give us r cos square theta plus r sin square theta. This will give me r. So this is the j. What is this j? It is dou xy by dou r theta, from which we can write dx dy is equal to r times dr theta. So each time we use polar coordinates, the transformation of dx dy to r dr theta happens where r is the Jacobian that we just found out. So what has happened now? I'm going to use all this information and insert it in my problem. But the only thing is, I'll be having to fix limits for r and theta because there will be no more x and y's in the problem. Those disappear and r and theta come. So what would be the limits for r and what would be the limits of theta? So I'll fix those limits by looking at my figure and then evaluate the integral. Dear friends, now come the critical stage of the problem where I'm converting this Cartesian double integral into a polar double integral. Basically, the idea is not to evaluate, that's not the main purpose. It's only to tell how the Jacobian is playing a part. And you can see the presence of Jacobian there. That is J. So, this double integral square root of x square plus y square over r, where the region is this upper semicircle, would be no change in the region, because simply because you change the variables, the regions don't change. But the variables are going to change. Square root of x square plus y square is square root of r square. That is already explained here. Then comes dA, that will become r dr dt. That is this. So this is double integral r square dr dt. So evaluation of this original double integral amounts to evaluating this. Both are one and the same. But you will find that evaluating this is much easier compared to this one. But if you want to evaluate, you must know the limits for theta and the limits for r. Let us look at the diagram. Theta starts from this radius vector, theta is equal to 0, goes this way. As it crosses the y-axis, it has swept an angle of 90 degrees. Then it continues the journey and ends at theta is equal to pi. So you can easily fix your theta limits. For example, if we were only working on the first quadrant of this circle, the theta limits will be 0 to pi by 2. Coming to the limits for r, because the circle has center at the origin, you fix r is equal to 0 as the lower limit. And this circle has got radius 4 and it has got fixed radius right through the journey. So the radius does not change because the center is at the origin. So the radius is 4 units. So r varies from 0 to 4. So theta is equal to 0 to pi, r is equal to 0 to 4, r square dr dt. I'm not going to evaluate this because there's already a lecture dedicated for this. What is the purpose of this lecture? How does Jacobian enter into your calculations when you use new variables in a double integration or in a triple integration? So anyone with the bare minimum knowledge of integration can complete this question. So please remember that the area element dA in Cartesian, which is dx dy or dy dx, becomes r dr d theta in the so-called polar coordinate system, where this r is the Jacobian. So that is the role Jacobian plays in double integration every time you change the variables. So let me present a second example.